Alrighty, last time we finished up with the inclined plane, and so we are going to continue on. And the next simple machine that we are going to talk about are wedges. So wedges, generally speaking, are V-shaped objects whose sides are two inclined planes that are sloped towards each other. A pretty common example of this is an axe. And so, generally speaking, when you're swinging an axe, if you bring it down on a log, you are providing input force downward, which means your outward force is going to split the wood into different directions. And so, generally speaking, just some extra things to know about this is that I gotta write this out. Thin wedges. So thin wedges have greater ideal mechanical advantage than thick wedges. Okay, providing that they are of the same, I don't know what that was, of the same length. Okay, so say for example, I have this wedge right here. If I have a wedge that is more narrow, it is going to have a greater ideal mechanical advantage than this larger wedge. And if you think back to the inclined plane that we talked about in the last video, that's because the steepness or the slope of my inclined plane is less, and so it is going to create a greater advantage versus something that is coming at it from a really, really wide angle is not gonna do a lot of damage. So those are your wedges. Again, axes are a really good example of this, or if you look at the head of a flat screwdriver, that's technically a wedge because you have like a very narrow tip, and then it would come outwards, but it has enough to where it would fit in the screw nicely. So just some examples of wedges. And up next are screws, now that I talk about it. And so screws are in inclined planes that are wrapped around a cylinder, and so I've done my best to draw a wonderful little example. It's really hard to show the input and the output force on this one, just because when you think about the inclined plane, it's all regarding these little threads. So fun fact, the turns that are around the turns, they're there, of the inclined plane are called threads. Okay, so all of these little things right here are called threads. And so the closer the threads are to each other, it gives you a greater ideal mechanical advantage. So right here you can see that my threads are pretty close to each other versus if I had a screw and my threads were much further apart, this would not hold near as well as something with a thinner screw would. There's a couple of different ways to think about that, take it as you will. But I personally like to think of it as there are more screws, so it is going to hold more frequently than just a few larger inclined planes. So those are screws. And now we're on to the fun one. Alright, so pulleys. similar to the levers, pulleys have 3 different types. But the key feature between all of these is that they're going to consist of some sort of rope that is going to fit into the groove of a wheel. And for all of the pulley systems that I'm going to talk about, your ideal mechanical advantage is going to be equal to the number of rope sections that are supporting to the number of rope sections that are supporting the load being lifted. That's an awful. There we go. Lift it. There we go. So again, we're gonna take a look. Whoops. Sorry, I'm trying to read examples from the textbook so that I'm telling you everything properly. So let's take a look at what each of these look like. But key thing with all the pulleys is that it's a rope and the groove of a wheel, which I did my best to draw and represent, and that the ideal mechanical advantage is the number of rope sections supporting the load being lifted. So let's take a look at the first one. So I actually need to make sure that I have, there we go. Okay. And yes, the section is collected. All right, so if I'm looking at a fixed pulley, this is the first type of pulley, and it is when I have a wheel attached to a fixed location. So right here, for example, I have a ceiling, and on that ceiling is where I have the wheel attached. And so generally speaking, your input force is going to be where you are pulling down. And so I would be pulling, so we'll draw a little me right here, and then we'll give me a little bit of hair. And I would be pulling on this end of the rope right here. Looks like I'm holding a lollipop, but I'm pulling on the end of the rope. And so the tension that is pulling down on this side of the rope is also on the other side. And so let's say I am lifting a box that is 4 newtons. Okay, well, when I pull down on this rope, I'm going to pull down with a force of 4 newtons, and so when it pulls up on the other side, it's going to pull up with the exact same force. So when we're looking at a fixed pulley, it changes the direction. So it changes the direction, but not the size of the input force. Okay, and so in this case, your ideal mechanical advantage is always, that's not a W, always equal to 1. Because if you see, I'm pulling down with 4 newtons, and it is pulling the box back up with 4 newtons. So 4 divided by 4 is equal to 1. A common example of this is for those that are in ROTC or JROTC and they take the flag out when they are pulling down on the rope to lift the flag up, or even if you're at home and you're lifting up the blinds have weight and you're pulling it up with that weight. So those are all examples of a fixed pulley system. The next one is a movable pulley. So in this case, this might be one where I have a rope attached to it, and so I'm maybe up at a higher level, and so I need to pull something up. And so again, we'll pretend that I have a 4 Newton box being pulled down by gravity. Well, I only have to pull up using 2 newtons because that weight is evenly distributed between where it is fixed and where I'm pulling up. but the wheel itself is moving as I pull up. And so this one is nice because it changes both size and direction. Okay, and because of this, we can see that I have two different forces pulling up for one force pulling down, and so your ideal mechanical, that's not an A, advantage in this case, just for this one for example, is 2, because, or generally speaking, it's going to be 2 because I have two forces that are pulling up against the one. And so most of the time your movable pulley will exert 2 times the output value as the input. Okay. And so both sections are going to pull with the same amount of force. So I'm going to abbreviate. So both sections of your rope, it's a weird looking R. Okay, so like I mentioned earlier, both of your rope sections are going to pull with the same amount of force, and because of this, it's going to exert twice the amount of output to change both the size and the direction of the weight being lifted. And last but not least, for your pulley system, this is the fun one, is the pulley system. So this is a very complex structure, but it's a really, really good example. So if anybody has seen it, Dr. Stone does a really, really good example. It's a really nice show. Person, spoilers I guess, gets trapped, and another person uses a pulley system to help get whatever is crushing the person off. So the pulley system is really, really nice because it combines a movable pulley and a fixed pulley to achieve a large mechanical advantage. So there's not a set number to this one, but recall what I said earlier, your number of rope sections is what is used to determine what your ideal mechanical advantage is. So if I'm over here, so draw me again over here, and I am pulling on, get myself a little bit of hair. My hair has grown a lot. So I'm pulling on this system. I have 4 different sections of rope that are pulling up my box right here. And so I guess you could say the input force, the force that I am pulling on, is just this one lever right here, but then you have 4 different sections of output forces that are being exerted. And so just add up your number of sections. So there we go. So add number of So add your number of sections of rope to determine your ideal mechanical advantage. So in this particular case, I have 4 times the output. And yeah. Oops. There we go. And so that is it for all of these simple machines. Compound machines are basically when you take a combination of 2 or more simple machines that are operating together. And so basically I can take a lever and I can take a wedge, or I can take a pulley and I could take a screw. Just taking any of those in combination is what makes a compound machine. So, oops. Thank you guys for being awesome. Love you all so much. Y'all take care, and I hope you enjoyed.